All right, for this video, we're going to be talking about some rotation. We're going to go through a common rotational statics and torque question, move into some rotational kinematics, see where this question can go, move into dynamics and energy. So how does energy problem change when there's something rolling? And then we'll get into angular momentum and its conservation, where we focus on the angular momentum of a point mass. A couple things to always keep in mind when you're doing rotation, sometimes referred to as angular, is you keep in mind your translations, where you go from your more common linear terms into your less common angular terms. Yes, I did make a mistake. Sorry. So a common torque problem that would be done in rotational statics problem is a hanging sign. So we'll go through something like that real quick, talk about some formulas along the way, and see where we go from there. So we have a mast beam that's hanging from some point. Let's just have it hang right at the end. That'll make all of our stuff do okay. There's a hinge right here. And then what we want to be able to do is, let's hang a sign on it. We'll just hang an extra sign on it. Let's hang a sign right here. So what makes this different than a translational equilibrium problem and only a translational equilibrium problem is because this beam wants to pivot, this wants to rotate down because of its weight and the weight of this sign. However, this tension force is holding it back. So we want to be aware of a few things, that the torque is how much force is exerted some distance from the pivot point. So the force that causes a torque on this system because of this mass acts right here at the end, which is the whole length of the beam away from the pivot point. So this exerts a lot of torque. If the mass were located over here, it would exert significantly less torque because the distance it's from it would be much smaller. So there's a direct relationship between the length and the torque. Some questions might ask, if I pulled it down or I pushed it in, that does have if I pulled it down at an angle, or I pushed it in, that does have a long length, but it would have very little torque, especially if you were pushing parallel to the pivot point, because it wouldn't attempt to make it rotate. It would push it into a non-movable object. So the force must be perpendicular to the lever as well to maximize torque. All right. So anytime you're doing this type of problem, what you would want to do is you'd want to identify all the forces acting on the system. And the forces that are acting on this system would be the force of gravity from the beam. Note that I put it right in the center. As long as it's a uniform distribution of mass, the weight of the object will act right in the center. All of the other forces that are acting on the system happen to be located attached to strings. So I'm just going to refer to this one as a force of tension. And then I'll call this one the force of the sign, the force of gravity from the sign. So we got the beam, the sign, and the tension. For the rotational standpoint, there's another force that we don't concern ourselves with, but if you're asked to draw a free body diagram, a force diagram of the situation, you want to make sure you take into account the forces that are acting at the hinge. And the forces that are acting at the hinge are acting up and to the right. We'll get into the forces acting at the hinge after we finish the first part of this question, but we would want to identify that there is a force there just in case they were to ask. A couple other things that you would need to be provided to solve the rest of this problem is the length of the beam, which we'll just define as L for our purposes, and the angle theta here, which we'll just call theta for our purposes. So I have two forces that are attempting to make the system rotate clockwise and one force that's attempting to make it rotate counterclockwise. So clockwise forces would all have to have the same sign. and counterclockwise forces would all have to have the opposite sign of that. What we would do next is set up an equilibrium statement. It looks similar to what you would have done with Newton's second law. However, now instead of taking into account forces, we're going to take into account torques. So we know that it's not rotating down, or not rotating clockwise, or not rotating counterclockwise. So we're going to set that torque equal to 0. And then we're going to identify the forces that are making it rotate clockwise. So this is a clockwise, this is clockwise, and this is counterclockwise. All right. So what we're going to do next is we're going to say that we have one clockwise force. So we have the force of gravity of the beam, but we need to take into account the length. We haven't taken into account how far away that's acting from the pivot point. So it is acting L/2 away from the pivot point. Half of the length. In addition to this clockwise torque, there's another clockwise torque, the force of gravity from the sine. And it is acting L away from the pivot point. Those two forces are in the same direction, so they're both the same positive sign. Alternatively, there is one force that is acting in the counterclockwise direction, so we want to say that it has to have the opposite sign, so I'm going to put minus, and then I'm going to write it down here so there's plenty of space. The force of tension, but notice how it's not acting perpendicular to the beam, it's acting up and to the left. The left component possesses no torque because it's parallel to the pivot, but the vertical component does, so we want to identify the vertical component of this force of tension, which in this case is Ft sine. So we'll say Ft sine theta. And then how far away is Ft sine acting from this? It's acting L away, so we've taken into account our R and our F for our three torques, 2 clockwise, 1 counterclockwise, and when we combine them, we find them to be equivalent to 0. With this, depending on the information you're provided, you would be able to identify any one of these unknowns because we only have one statement of fact, system of equations from your Algebra 2 class. But I can do one thing. I can identify that the length of the beam is in every one of these terms, which is nice by keeping it as L/2. So I just eliminate all of those, and that is an unnecessary value to know. Notice that the 1/2 does stay. They reduce to 1 when you factor it out. Okay, so now you could look at that and identify that you have that as a statement of fact. So I'm going to write that one statement of fact up at the top, and then we're going to look at something else that we would be able to do at this point as well. So we have the force of gravity of the beam divided by 2, plus the force of gravity of the sine, minus the force of tension, sine theta, and that equals 0. And we got that from our rotational equilibrium statement. What you need to do there is you need to identify the torques that are acting clockwise and the torques that are acting counterclockwise. But there is translational equilibrium taking place as well. There are forces that are acting down and there are forces that are acting up. But the system isn't accelerating down, nor is the system accelerating up. In addition to that, the system isn't accelerating to the left, nor is it accelerating to the right. So you can write two other statements of equilibrium, and that would be our translational statements of equilibrium. So we have the force in the x's, in the x dimension, that's the left and right, the horizontal. And we set that equal to 0. And then you would identify the forces that are acting to the left and the forces that are acting to the right. There is one force acting to the left, and that force is the force of tension cosine. This cosine component of this tension is a little right triangle here. The horizontal component acting to the left is the force that's to the left. But if there's ever a force to the left and we're not accelerating to the left, then we should be reminding ourselves of just what equilibrium is, and that's that there must also be then a force of equal amount to the right. So we want to say the force of tension cosine theta must be equivalent to whatever this horizontal force is in the x. Notice how this arrow is pointing up and to the right. That means that there would be a force pointing to the right. This arrow is pointing up and to the left, so there's an up component and a left component. We're just saying that the left component of this tension is equivalent to the right component of this hinge. So I'm just going to call that FHX. After I've completed that, I would then move on to defining what's going on in the y dimension. There's a little bit more going on here, but it's still not accelerating down, nor is it accelerating up. What we would then find out is that there are two forces acting down and two forces acting up. So I'm just going to say the force of gravity of the beam plus the force of gravity of the sign minus the vertical component of the tension, Ft sine theta, the tension, minus the vertical component of this, because that's also acting in the upward direction. You could think of this as potentially a frictional force, but since there's a hinge, there's like a screw in there preventing it from sliding down, it would be a normal force, just like this would be a normal force acting to the right. We would say that is FH in the Y. And when I add those together, I find that they sum to 0. Now what we have the ability to do is we can identify a few more things. We can set up a system of equations where we have many variables, and we can do lots of substitutions if we had to. But those three statements would then get you to be able to solve this problem, knowing significantly less than you might have initially thought you had to. Okay, so just keep that in mind. That would be all the rotational equilibrium and translational equilibrium you would be able to do to this problem. What then begins to take place is they make it move. So what they would do at this point is to challenge your understanding of physics, is they would cut this string. And what does that mean as they cut this string? Well, as they cut this string, there is no longer a counterclockwise torque preventing it from rotating clockwise. As a result, the two forces that are pulling it downward will make it rotate clockwise about this pivot point. But how much will it accelerate? How much will it rotate? How fast will it get? How long will it take it to get fast? Well, we would need to go back to our original statement and say these two are the only torques that are making it rotate. So let's go back to now a new statement. Getting rid of this one because now we've removed a tension that's no longer in the system. We don't have to worry about the hinge because the hinge doesn't exert any torque. There's no torque about the hinge. So I have the torque, and it is equal to I alpha. So what is that? Where am I thinking about that from? Well, remembering second law, we know that F equals ma. Our translations, mass is how hard or easy it is to get something to move or stop something from moving or accelerate. Its tendency to maintain its current state of motion. Well, moment of inertia is how easy or hard it is to rotate something or make it angularly accelerate. So that's what the A is. So anytime you have a linear acceleration, you can translate it to angular acceleration. The mass would translate to I, the moment of inertia, and T, torque, would be the rotational or angular analog to the linear force. So this is just F equals ma in rotational terms. The two forces that are making it rotate would be Fg of the sign, or Fg of the beam, excuse me, times the distance that it's acting from the pivot point. So that's Fg L over 2. The other torque that's making it rotate would be the force from the sign, but it's also acting all the way at the end. And then that would equal I alpha. So when you are thinking about this as I alpha, we would need to identify what I is. I is the moment of inertia of the system. So let's go through how we could find the moment of inertia of this beam. We have identified that the pivot point is located here on the left. So I'm going to do another calculation down here so I can identify what that moment of inertia is. The moment of inertia is if I added up all the little masses of this object. and how far they are from the pivot point, I would be able to do that. So sometimes you see it as the sum of mr squared, but since we have a beam that doesn't have chunks of mass, it's a uniformly distributed mass, we would have to say that it's the integral of r squared dm. So that's kind of an ugly statement. Notice that the variables aren't related, like they are related to each other, but not obviously here. So we're going to have to make a substitution and then identify a few things before we move on. Because this is a uniformly distribution of mass, we can do something right here immediately. And we could say that the mass per unit length is constant for this beam. And if I wanted to know the little bit of mass that was located right here, I would need to know its mass per unit length and then how much little length is right there. So I'm going to say that that little length is just dr. And now that if I said I had this little length and I multiplied it by that constant, that mass per unit length, the linear density, if you will, of this beam, then I would know the little bit of mass. So now that I know the little bit of mass in a constant term and a little bit of r, it's a little helpful here because now I can relate this r squared to dr. So then I make that substitution, and I've got the integral of over L r squared dr. I just substituted this dm with that. For this purpose, we know that the mass per unit length is a constant. It's a uniform being the same throughout, so we can pull that out of our statement. And I can move my integral now over here. What we would then do is identify the integral of r squared with respect to r is 1/3 r cubed. So then we would say that this statement right here would be equal to m over L r cubed over 3. But we haven't done one thing that we need to do. We need to evaluate. This should be, oh yeah, that's L. That's still L. It's L from here. We need to evaluate those bounds. So we haven't done our, we haven't evaluated our integral. We just have this. This is what the integral would be, but we haven't found the bounds. So what are the bounds? Well, we want to take where, or with respect to the pivot point. So we know that this whole, this is all L. And we want to start, I don't know, like let's start right over here. So everywhere from here over, well, this would be 0 L, and then this would be all L. So I'm going to put a 0 right here, and I'm going to put L right there. So I'm going to do it from 0 to L, the length of the beam, which we defined earlier as L. When I do that, I find that this would end up being, I plug in L here, and that equals m L cubed over 3L. Because my final is L, my initial is 0. When I plug in 0, it doesn't do anything. And then I can see that this L cancels out with that L up top, one of the 3 L's up top, and I get mL squared over 3, which would define the moment of inertia for a beam about its pivot, a uniform distribution of mass about one end. We'll do a secondary problem showing that you can use this idea to define the moment of inertia anywhere along that beam. But that's not the only thing that makes this easier or hard to rotate. There's also this point mass that's acting on it. So one thing that you want to do, if I was worried about all the mass of something, I would just take all of the objects that are there and I'd add up all the masses and I know the total inertia of that. But this is something that's rotating, so I need to take into account all the rotational inertias. And it's not as complicated as it sounds because you just add them up. So we now know the moment of inertia of the beam, but what's the moment of inertia of this? Well, it's just a point mass. So we take our mL squared of our beam, and then we add to it the other objects. In this case, there's only one other one. And the moment of inertia for a point mass is just the mass and how far it is away from the pivot point squared. And now we've identified the moment of inertia for the whole system, which we can plug in right there. And now we know the angular acceleration of the system. So keep that in mind. All these terms are the mass of the beam, the mass of the beam, mass of the sign. That should probably be there just to keep that in mind. I want to do one more thing here before we start talking about rotational kinematics. But now we've accelerated this system. If you had a beam, we just found the moment of inertia about this pivot point. But what if I put the pivot point right here? I don't know, we can put it right here. That's fine. So what we would say is we need to figure out how far, we know the whole beam is L. And let's say I put it L over 3 away from one end, which means the other end would be 2L over 3. Okay, so how far away is this end from the pivot point? How far away is this end from the pivot? And we also have to identify that this one's to the left of the pivot and this side's over to the right of the pivot. So when we integrate, we're going to start with our initial moment of inertia statement that says r squared dm. Make the substitution that we made on the previous work. Where we substitute dm with m over l and dr. And then we would need to know our bounds. In this case, our bounds are going to be from the left end all the way to the right end, but this is to the left of the pivot point. So we need to take into account that that's going to try to make it rotate a different direction than this would try to make it rotate. So we want to say that this would be negative L over 3. And the top would be 2L over 3. So our bounds are negative because it's on the left and positive 2L over 3 because it's on the right. You then do the integration, substitute your values, plugging in your bounds, and then you know the moment of inertia there. This technique allows you to find the moment of inertia for anywhere along this beam. So I can move it over here, I can move it here, I could have it 1/6 of the way over here and 5/6 of the way over here, and then my bounds would be negative L over 6, and then my other bound would be positive 5L over 6. L over 6 over here, negative, and 5L over 6 if I was on the right. So keep that in mind. How far away is it to the left? How far away is it to the right? On the one on the left, we can make negative. The one on the right, we can make positive. And that helps you find the moment of inertia for any uniform distribution beam. If it's a typical common shape, what they can do is they would give you the, they tell you it's a sphere, solid sphere, it's about 2/5 mr squared. If it was a disc, if it was a washer, a cylinder, those things are all found in a chart, and I would suggest that you look into that and look that up before you and have access to that anytime you're working problems out. Okay, going back to some common formulas from earlier units, we have our linear kinematic of the slope of a velocity versus time graph to tell you the acceleration. Change in velocity over change of time is acceleration. But what do these translate into to give us our angular quantities? So anything that you could do with this statement, you could also do with an angular quantity. So we want to make sure that we're ready to translate those. That's good and squeaky. So we've got the velocity translates to angular velocity, which would be omega. So I'm just going to take that and I'm going to turn it into omega, the final speed. When you turn on a fan, it starts at rest and then it gets to its speed. You could use this with time to figure out its angular acceleration. Omega naught plus alpha t, where our angular acceleration is alpha and our linear acceleration is a. So you just translate. This works for all the kinematics as long as you have constant angular acceleration, and that would be our alpha. So the other one that I would say is effective is if I wanted to give you the other term, we would want to think about, I write it as delta x, the change in position, not x and x naught, v naught t plus 1/2 AT squared. Notice that the position, if you're accelerating, is a quadratic position versus time as a quadratic with acceleration. So what's this turn into? Well, instead of being x, it's going to be theta, the angular displacement. How many radians did it go through? Omega naught t plus 1/2 alpha t squared. And then what you could do is, now that we knew the angular acceleration of the beam that we worked out right at the beginning, we could then apply kinematics to figure out the angular speed after some amount of time. We could figure out its angular displacement after some amount of time. And you could even find out, without knowing the time, you could say that the angular speed would be related to omega squared, the angular speed squared, equals omega naught squared plus 2 alpha theta, which is another kinematic that kind of comes from conservation of energy. So something to think about there is, if it said how fast is it going after it rotates through pi radians, which that one wouldn't, it'd rotate through pi over 2 radians, but that's neither here nor there. So it's also not under constant angular acceleration in that previous question, because the torque, the weight of the objects don't necessarily always act perpendicular to the pivot point. So I want to make that clear. It would only be an initial angular acceleration. All right. So we've talked about torque, rotational statics, just basic rotational kinematics. It is as simple. I don't know if it's simple, but it's not a difficult concept when it comes to just identifying your variables and identifying which kinematic to use to figure out the unknown quantity. But what about the dynamics and energy? So we have the dynamics with, we got that system to accelerate after we cut the string in our statics question. But what if I had a ball that was rolling down an inclined plane? Most of the time, if we did an object, we would have used a frictionless surface with a rectangular prism, so that it would just translate through. We could do lots of things here. We could draw a free body diagram. Friction is what causes this to rotate, so don't forget that if you're looking into that. There's a question from a couple years ago, AP exams, that you might want to look at. I think it was the 2018 AP Physics C exam, maybe the 27th AP Physics 1 exam as well, where they talk about drawing that force diagram. So you might want to take a look at that. But if I wanted to figure out how fast this object is getting here, I need to take into account that it's going to be rolling as well. So I'm going to say that here it starts with height, which I want my students to identify immediately as gravitational potential energy. It starts with UG. But that UG, by the time it gets down to the bottom, that potential energy turns into kinetic energy. But it's not just going to be translating through space, it's also going to be rotating through space. So I'm going to put KT for kinetic energy, the translation, the center of mass as it translates through. But it's also going to be rotating. So that is a form of energy that we need to take into account, because it takes more energy to rotate than it does to not rotate. So I put, okay, rotation. We started the same way. We identify that it has mgh, where we have the mass of the object, the gravity of the planet that you're on. In our case, gravity is about 10 for Earth, and the height that our initial ramp is at, or how much higher it is than our bottom, I think is a better term. And then we already are aware of the translational kinetic energy, 1/2 mv squared. But what does that turn into for rotation? Well, we have an analog for mass when it comes to rotational or angular quantities, and that is I. And our analog for velocity is omega. So that's your rotational energy addition. You do a few things here, and I want to make one other thing. A nice translation is arc length. depends on the radius, and angular speed depends on the radius. If you're spinning in a circle, where you are on the circle depends on how fast your translational or linear speed is. The farther you are from the center, the faster you're moving linearly, but you're moving the same speed angularly. So we want to take into account that the angular speed is the same for everything on the object, but your linear speed is dependent upon r. And to do that, you simply just need to multiply your angular speed times r to get the v. In addition to that, you could say that omega then must equal v over r. And I think the easiest way to think about this is in terms of a circle. A circle has an arc length of 2 pi r. That's the circumference. So that would be the total length around. But what's the theta to go around a circle? Well, the theta, this would be like x. How far did you move like x? It's not exactly x, because if it's x, it's displacement, and it would be 0. 2 pi is our theta. So how did I go from my theta to my x? I just multiplied my angular quantity by r. So angular quantity times r equals v, and then I divide the other way around to get the other way. So that's something to think about, an easy translation if you just think about circumference versus radian. This is a sphere, solid sphere, so I can already identify that the moment of inertia for a solid sphere is 2/5 mr squared. And let's do some plugging in and see what we come up with. I got mgh equals 1/2 mv squared plus 1/2 times the quantity 2/5 mr squared times omega squared. But I'm going to plug in omega squared as v squared over r squared. So the I is here and the omega is here. Note that now that I've translated this moment of inertia into its base form, I can see that mass is in every term. It reduces to 1. And I can see that the radius of the object cancels out right there. This velocity and that velocity are the same value. So that helps, because now I can say that my GH, the amount of energy I began with per unit mass, is equal to v squared over 2 from here, plus 2/5 times 1/2 is 1/10. V squared over 10. And now I've taken something that looks like it has a tremendous amount of unknown variables, using a table to find this one, and a quick calculation, I've eliminated several of those variables and identified it just to be dependent upon those. How does this problem change? It depends on what this object is. If this object is a larger moment of inertia or a smaller moment of inertia, it affects this velocity. Notice that if this number is bigger, this coefficient right here, this 2/5, if it's bigger, if it's 1, then more velocity is located here. So keep that in mind. That would be a follow-up question. Would the kinetic energy be, or would it be traveling faster at the bottom if I change the moment of inertia of this to be larger, to be smaller? Something to look at, something to keep in mind. Last thing I wanted to talk about with this question is if it leaves the table, it doesn't gain rotational energy. It doesn't gain or lose rotational energy. And that's because it's rotating one direction, and it's in rotational equilibrium at that point. Right now, it's not in rotational equilibrium because of friction, but here it would be in rotational equilibrium because the force of gravity acts right at its center, which exerts 0 torque on it. You can also think that the force of gravity is distributed across the mass so that some of the force of gravity is over here and some of the force of gravity is over here, canceling each other out, because if it's rotating one way, this is attempting to slow it down and this is attempting to speed it up, or vice versa. So on its way down, it doesn't gain rotational kinetic energy. So at this point, after I found out the velocity it leaves the table, that's the velocity it's traveling initially here. It does gain kinetic energy because of weight and the potential energy turning into it. However, it doesn't gain rotational energy, rotational kinetic energy. All right. The last thing I associate with rotation introductorily is angular, and that's with angular momentum. So I start with our base idea of momentum. Our base idea of momentum is P equals mv. You do lots of conservation of momentum questions. The most effective technique to start a physics problem because it's conserved. How does that translate into angular momentum? We take that P and we turn it into an L. We translate the m into the moment of inertia I, because that's inertia in the linear state, and then v is the velocity, so we just translate that into omega. Now I've got my angular momentum as I omega. We've already described how to do find moment of inertia for beams. If it's something else, we can look into that. A common example that I do with my students is I have a spinny chair. I imagine most AP classes would do this. I have a spinny chair that students hold books, and they manipulate where the mass is located. So when their arms are out, we want to identify that they have a large moment of inertia because the mass is far away from the pivot point, and as a result, they travel slowly. So when you have a big moment of inertia, you have a smaller angular speed. And we're going to talk about this conservation in a second. When my students pull their arms in, what happens is the moment of inertia decreases because now the mass is no longer away from them, it's closer to the center. So, and when we're thinking about mr squared, our r value has gone down. It's squared, so it goes down quickly. So our angular, our moment of inertia goes down. As a result, my students go woo, and they giggle, and sometimes they fall out of chairs, and the angular speed goes up. Well, what do we see? What's going on here? Well, we know that the momentum is conserved in a system as long as the forces are all internal, and here what happens is that's the case as well. Our angular momentum does stay the same. A figure skater does this all the time. It mesmerized me as a child. I didn't know how they did not vomit all over the place. I still don't. But now I know why they can spin more quickly and slowly. The moment of inertia change causes their angular speed to change, and because this went down, this had to go up to maintain the same moment of inertia. So that's an initial idea about conservation of angular momentum. Lastly, a tricky question. I have a beam, it pivots up here. We can identify its moment of inertia. I believe we've identified that as ml squared over 3 at this point. So I'm just going to write that just as a quick idea. But what happens is, what if I threw a ball at this hanging beam? And what would I have to do for that? So there's going to be a collision. And when we think about a collision, we think we got to think momentum. So how do I take a linear traveling object and turn it into a rotating system with momentum? So we want to figure out how we can identify the angular momentum of a point mass. And we know that's I omega. And where r would be the distance from the pivot point, and the pivot point's all the way up here. So right now, the r value is right there, if you wanted to think about what I'm about to do. So we got mr squared, because it's a point mass. We talked about that with the beam problem. And omega, well, this is just translating, so I'm just going to write it as v over r. When I do that, I can immediately eliminate one of the radius values, and I got mrv. and that would be the angular momentum of a point mass. But it's weird right now because this velocity value v is not perpendicular to our radius, which is ultimately what we want it to be. Now you could write sine theta here or whatever you want to identify that the r value and the v value need to be perpendicular to each other. And you could draw a bunch of trigonometry and all of that stuff. But right now, less of the v is pointing perpendicular to this, but the radius is really long. Then when the more effective technique to find the angular momentum of this object about the pivot point, if we take it right here, right before impact, if we were to look right here, right before impact, the velocity of the object, as long as it's in free space, no friction or anything like that, it should be constant. It would not change. But what we would find is now all of the velocity is perpendicular to the pivot point. So I don't have to worry about taking that into account. But how is that equivalent to the angular momentum of this point mass right here? Well, right now the radius is really long, but the velocity isn't as much. Here, the radius has decreased because now it's only this leg of our initial right triangle. So this leg is shorter, but the velocity is more. The rate at which those change cancel each other out so that we see that this value of MRV doesn't matter where I take it along the way, because the radius value is decreasing as the velocity value is increasing with respect to the perpendicular. So the most effective technique to solve this problem is to just take it right there, right before it strikes it. So we would want to say right there, we want to say that the moment of inertia, or the angular momentum, of this ball is its mass times in this case, the length of the beam, which we'll define as r. I'll call this r1. And its velocity v. And now we have the angular momentum of this ball right before it strikes. Well, that angular momentum is going to cause a collision, and then the amount of angular momentum before will equal the amount of angular momentum after. And then we need to start doing a little bit of a problem. So right now, this isn't rotating, so we start with this much, and it turns into something. Let's say it sticks. That makes it a little bit, let's say it doesn't stick. Let's say it bounces back, and I want to know a couple things, and you would have to be given a little bit of extra information. So it's initially to the right. Which way is this beam going to rotate? It'll rotate to the right, and I want to call that I omega, right? But which way is the ball going to go afterward? It could bounce off. So if it bounces off to the left after the collision, we would want to put minus MRV F, right? Because if it bounces off, it's going to be momentum in the other direction. We want the same amount of momentum before as we did after, so keep that in mind, the vector direction aspects of that. This would rotate to the right, this would rotate to the left. Notice that they're in opposite directions. They have to have opposite signs. And this is already to the right, so these need to have the same signs. Before equals after. And there you go. What about if they stick together? If they stick together, we need to take into account the total moment of inertia of the system. So this is now if they stick. So if they stick, the total momentum or moment of inertia of the system would be the moment of inertia of this as it sticks to it, which would be mr squared, point mass, plus the moment of inertia of the beam, which about its pivot point is mr squared over 3 as we determined before. And then we multiply that by omega. So this would be one object colliding and sticking with something. In linear terms, it'd be mv equals m plus mv. But we need to translate that into angular quantities. So we need to take instead of being mass, we're looking at the moment of inertia. And then from there, it's an algebra problem. A couple things to think about. Hopefully you find some use of this. If not, no big deal. Thanks for your time. Have a wonderful day and stay safe.